everyone, and welcome to another explainer. So, have you ever actually stopped and wondered how you can stream a massive, high-definition movie right to your phone? Or snap literally thousands of photos without your device instantly throwing a storage full error? Well, it turns out you're interacting with one of the most brilliant tricks in computer science every single day. Today, we're focusing on demystifying image compression. Think of this explainer as a bit of a detective story. We're going on a hunt to track down wasted digital space, figure out exactly how it hides in plain sight, and see how these clever algorithms just eliminate it without us ever even noticing. Here is our roadmap to crack the code on bloated files today. First up, data versus information, then why we need compression, followed by lossless versus lossy compression. After that, we'll hit the 4 data redundancies, the math of compression, and finally, cracking Huffman coding. Let's dive right in. All right, section 1, data versus information, the root of the problem. To really get how image compression works, we kind of have to change how we think about what a digital image actually is. The crucial point here is understanding that data is simply the raw delivery mechanism. It's the heavy, clunky building blocks of a digital file. In an image, data usually takes the form of pixel gray level values, basically numbers telling your screen exactly how bright a microscopic dot should be. But data on its own, it's just raw, unrefined numbers. It can often contain completely unnecessary, irrelevant, or just repeated bits that offer literally zero real value to the human eye. We call that extra baggage redundant data. Now, on the flip side, we have information. This is the actual meaningful content that we actually care about. It's this sort of elusive concept that only comes to life when data is interpreted correctly. It's the face of your friend in a photo, right? Or the readable text on a scanned document. The meaning completely depends on what the application actually needs to extract from those raw pixels. So notice how data and information are mathematically and conceptually not the same thing. Data does not equal information. And honestly, this distinction is the exact loophole that compression uses. If we can just strip away the raw data that isn't pulling its weight, we can drastically reduce the file size without actually destroying the underlying meaningful information. Moving right along to section 2, why we need compression, the rising stakes. Because out in the real world, the stakes are incredibly high. Think about the sheer weight of modern files. High spatial resolution, increasing bit depths, multiple color channels. In fields like multimedia streaming or satellite imaging, this creates an explosive demand for storage and bandwidth. Imagine a hospital trying to store tens of thousands of high-res MRI scans or satellites beaming continuous massive visual maps down to Earth. If we didn't compress these images, our transmission systems would completely choke on the bandwidth required. Our storage databases would fill up in an instant. Compression is absolutely crucial to make modern digital life function. Which brings us to section 3, lossless versus lossy compression, choosing our weapons. To solve this bandwidth crisis, we have to decide just how aggressive we want to be. Let's weigh what we're willing to sacrifice for the sake of space. With lossless compression, we preserve the data exactly. There is absolutely no permanent information lost. The decompressed image is a pixel-perfect recreation of the original, but the trade-off is efficiency. Lossless typically only squeezes files down to maybe a 2-to-1 or 3-to-1 ratio. On the other hand, we have lossy compression. Here, we basically accept that some data will be thrown away forever, meaning you can't recreate the original image exactly. But in exchange for that slight dip in quality, you get massive space savings, routinely hitting 10-to-1 or even 50-to-1 ratios. For lower quality stuff, we can even push that to an astonishing 200-to-1 ratio. It's really all about choosing the right tool for the job. Okay, section 4, the 4 data redundancies, identifying the suspects. If we want to understand how compression works, we have to identify the specific culprits causing these bloated files. We've got 4 specific ways information is repeated more than necessary or just ignored by the human eye. Number 1 is coding redundancy. That happens when we use way more bits than necessary to represent an image's intensities. Then we have spatial and temporal redundancies. Those happen when neighboring pixels are practically identical. And finally, irrelevant information, which is exactly what it sounds like. It's data that our human visual system simply doesn't perceive or care about. Notice how we can exploit similarities not just within a single photo, but across the video sequences you watch every single day. Say you take a photo of a clear blue sky. You've got massive spatial redundancy there because thousands of neighboring pixels share the exact same shade of blue. Why on earth would we store that identical blue value independently 10,000 times? Temporal redundancy takes this a step further in video. If you're watching a video of a person talking against a static background, the background pixels aren't changing from frame to frame. Good compression algorithms are smart enough to just carry that background information over rather than reloading it 30 times a second. Let's put some numbers to this in Section 5, the math of compression, proving the concept. We're going to use a simple theoretical image here. Imagine a tiny 3x3 grayscale pixel grid, just 9 pixels total. And let's say every single pixel has the exact same intensity value of 50. If we use standard 8-bit fixed-length coding for every single pixel in this uniform grid, the data weight adds up fast. To find the original image size, we just multiply the width of 3 by the height of 3 by the bit depth of 8 bits per pixel. Do the math, and that comes out to 72 bits of data. Keep in mind, this is an incredibly simple image. Every pixel is identical. Yet our computer is rigidly demanding 72 bits to hold on to it. But hold on, because every pixel shares the exact same value of 50, we don't actually need to store it 9 separate times. We can conceptually represent this entire uniform image with just a single 8-bit value. Boom, we just drastically reduce the file size down to just 8 bits. So let's expose the culprit. By subtracting our reduced size of 8 bits from the original bloated size of 72 bits, we've just found 64 bits of pure coding redundancy that was completely wasting space on our hard drive. And this brilliantly illustrates our compression ratio. By dividing the original 72 bits by the compressed 8 bits, we get a ratio of 9:1. Our original file was literally 9 times larger than what we actually needed to convey the exact same visual information. The data was heavy, but the information was simple. All right, final piece of the puzzle. Section 6, cracking Huffman coding, the master key. We have seen the math on a super simple scale, but now we need a master algorithm to handle complex images that aren't just one flat color. This one question forms the absolute genius foundation of our solution. In our previous example, an 8-bit code meant every pixel got exactly 8 bits, no matter what. But what if we broke that rule? What if we gave shorter codes to the pixels that appear all the time and longer codes to the weird outlier pixels that barely show up at all? This variable length strategy is known as Huffman coding, and it completely exploits frequency. If the color black appears thousands of times in a nighttime photo, Huffman coding gives it a tiny short binary code. But if a single bright red pixel appears just once, it gets a much longer code. When you add it all up, the most common pixel values take up the least amount of digital space, giving you drastically fewer total bits for the entire image. And the best part, Huffman coding is entirely lossless. Let's trace the exact steps the algorithm takes to pull this off. First, the computer analyzes the image and calculates the frequency of every single pixel intensity. Next, it throws all those frequencies into a priority queue, basically a list ordered from least to most frequent. Then, it starts combining the lowest frequency nodes, continually merging them together to build this branching structure called a Huffman tree. Once that tree is built, the algorithm just walks down the branches, assigning a binary 0 to every left turn and a 1 to every right turn. This generates a unique path and therefore a unique binary code for every single pixel value. Finally, it builds a Huffman table to officially map everything out, allowing it to instantly encode the image into a tiny file and decode it perfectly later on. So, the crucial point we keep coming back to is finding that perfect balance. The entire field of image compression is really just a balancing act between stripping away the heavy, redundant data that clogs up our networks and preserving the essential information that our human eyes or our medical scanning tools actually need to function. And that wraps up our investigation into the hidden detective story of digital space. Every time you snap a photo, algorithms are instantly hunting down redundancies, making split-second decisions on what stays and what goes. So I'll leave you with this. If compression means navigating the balance between perfect quality and infinite storage, what visual information are you secretly willing to sacrifice tomorrow? Definitely something to think about next time you're swiping through your massive camera roll. Keep learning, and I'll catch you on the next explainer.